Welcome to Chapter 10, Energy, Work, and Power. Good news, these are all words that you know and have heard of before. I know you are being an outstanding student and you've got your calculator, your notes, and your book open to page 290 all ready to go so that you can be an active and participatory student in your dorm room or from your cell phone or wherever you're watching this. So really fast in your notes, I want you to go ahead and make this table that you see with these three words, energy, work, and power. And I'd like you to leave room for your definition, the physics definition, the unit that we use, and any equations that you find in your book about these things. And I'm going to have you kind of go ahead and do what we normally do in class, which is give me your definition, and it can be your examples. I'd like you to do a little bit of research in Chapter 10 and find the unit that each of these is measured in. And I'd like you to jot down any equations that you find that we use to measure these different kinds of things. So just pause the video and go ahead and do that. All right, and I'm going to go on and give you the physics definition of all of these. I'm going to give you my definition, and then I will go through and do units and equations throughout the lecture. All right, so I will give you my definition, I will give you the physics definition, and throughout the lecture we'll do those things. Okay? So my definition of energy, and I'm going to use a big capital E for generic energy, is the stuff that makes stuff do stuff. And I don't have room right here to write that down, so I'll say it one more time. It is the stuff that makes stuff do stuff. And that'll make more sense here in a second. The physics definition of energy is the ability to do work. Right? And that'll make sense here in just a second when I tell you what the heck work is. Energy is something that is measured in Newton meters, which is a compound unit, so it's newtons times meters. And we effectively call this a joule, which we represent with the symbol J. Work is, I'm going to represent with a generic W to represent work in my equations. Work is stuff moving, right? And so that's my definition, just stuff moving. And the physics definition is things moving due to a force. Due to a force. There we go. Work can also be known as the change in energy, and so I'd like you to add that to your physics definition. It's things moving due to a force, or depending on your situation, and it's both really, but it might be more helpful to think of it this way, or the change in energy, right? Because it's the change in energy, work is also measured in joules. It's kind of like impulse and momentum. They're pretty much the same thing. And then power is how fast work gets done. We represent that with a P. And I'm going to say the physics definition is how fast work gets done. And the kind of complicated part here is that the unit for power is the watt, which we represent with a W. And so the only reason that's complicated is I'm using W for work and W for watt. And so you need to be able to keep those things straight and figure out what we're talking about. So just pay attention in the lecture. If there's a time involved, then we're talking about work. And if there's not a time involved, then we're talking about work. I'm sorry, if there is a time involved, we're talking about power. And if there's not a time involved, we're talking about work. All right. There are two basic types of energy, and you might remember these from high school physics or maybe even like middle school and elementary school physics. There are kinetic energy and potential energy. And so very simply, kinetic energy is just the energy of movement or moving things. And I'd like you to take a second and come up with a couple of your own examples. My example is going to be someone or something running. There's also potential energy, which we can think of as stored energy. It's things waiting to move or that could power something moving. My two examples are going to be food, because I love food, and gasoline. These things both have energy stored in the chemical bonds of that material. And we know, you know that food is energy, right? Without food, you wouldn't have the ability to run. It is what fuels you. And there's a chemical reaction in your body that breaks that down and makes it readily available for movement. Gasoline is the same thing. It's a highly volatile material, and we have processes in our engines, namely combustion or ignition, that release the energy stored in those as heat and allow things to move because of that. Okay. These are the two very, very broad groupings of energy, and so what I'm going to do is go on and kind of break these down into newer and more specific forms of energy that we can then talk about and calculate. And so take a second and go ahead and make this chart. In this chapter, we are really only going to talk about these four. The remaining 5 of these, chemical, electrical, nuclear, electromagnetic, and sound, these are all next semester. And so these are going to be in the spring. I want you to know what they are for now, just so you can have an idea of how things change from one to another. But the only ones that we're really going to calculate are these up here. And so there's kinetic energy, which is the energy of movement. And again, I'm going to give you the example of a runner. Okay. There's gravitational potential energy, which is the potential to move due to position or the ability to fall. If you're able to fall, you must be off the ground. And I know for uncoordinated people, this might not be true. But you need to be off the ground. And so maybe I would give the example of a climber at the top of a cliff that is about to rappel. They have the ability to fall or the ability to move because of their position. Climber, there we go, at the top of a cliff. There's elastic potential energy, which is one of my favorites. The example that I'm going to give you is a slingshot, or a rubber band is another good example. As you pull a rubber band back, like a little classroom slingshot, as you pull it back, that energy is stored in the rubber band, and it is up to you whether or not you're going to allow it to do work by releasing it. That elastic potential energy can then get converted into kinetic energy. And then the last one that we're really going to talk about a lot is heat or thermal energy, and I'm going to give the example of an engine. We will look at heat and thermal energy a lot more in chapter 10, but for now, for most of the things we're going to look at, heat and thermal energy is a byproduct. It's an inefficiency of types of energy. And so as you take your hands and you rub them together, you find that you have heat as a byproduct. It's not what's making your hands move, it's a product of that friction. Very quickly, a walkthrough of the formulas. K is for kinetic energy, M is for mass, V is for velocity, U is for gravitational potential energy, M is mass, G is 9.8, and Y is the position along the y-axis. U sub S is spring potential energy, is what that means. And then K is the spring constant. It's been a while, and it was a really brief moment of physics, but K is the spring constant that's usually given to you. And then X is the displacement of that spring. Thermal energy is equal to work, which is equal to force times distance, which is equal to the coefficient of kinetic friction. Ooh, that's an old one. And you're going to have to go back to chapter 4 or 5 for that one. And then delta X is change in position. All right, so let's go through some examples. Let's talk about the kinetic energy of a runner. Let's say I have a runner who is 70 kilograms. That's my go-to number for the mass of a person. And that they are running at 5 meters per second. And I want to know their kinetic energy. So kinetic energy is equal to 1/2 times the mass of that person times their velocity squared. And I square the velocity first because of PEMDAS. And so K equals 1/2 times 70 times 25. And remember that the unit for energy is the joule. And so I will do, let's see, 0.5 times 70 times 25, which is going to give me a net energy of 875 joules. No naked units in physics. Always, always, always put the unit. I also want to make a side note here that joule is the SI unit for energy. And so the joule is the SI unit for energy. Just like in the States, we use feet instead of meters. In the States, the customary equivalent of this is the calorie. And yes, like the calories in your food, right? And so joule is what we'll be using in physics. It's what's used around the world. And then if your mind is wondering and saying, well, okay, what if I buy, I associate calories with food. So if I buy a candy bar in England, is it then measured in joules? And yes, it is. Food is measured in joules of energy everywhere else that uses the SI system except the US, and we use calories, right? But again, in physics, we're using joules. So, interesting side note. There is gravitational potential energy. You may also see this sometimes as U sub G, which means the gravitational potential energy. And so don't be freaked out when you see this. That's nothing new. Let's say I have a roller coaster, right here, that is 30 meters tall. And so it's 30 meters tall. And the cart has a mass of 2,500 kilograms. When that cart gets to the top of the hill, what is the gravitational potential energy of that cart? And so I will do the mass of the cart, which is 2,500 kilograms, times G, which is 9.8, not negative 9.8. Remember, G is just the absolute value of the gravitational acceleration constant. And then Y is, let's see, 30 meters is the position off of the ground. And so I will find that this roller coaster has a total energy of, let's see, 735,000 joules, and that is its ability to fall. And I know you guys have probably all been on a roller coaster at some point, and you know that roller coasters actually take kinetic energy. And so down at the bottom, you would be going really, really fast. And then as you climb up, that kinetic energy begins to slow down because it's getting converted into potential energy, and you pause right at the top before you pick up pace and go all the way back down to the bottom. And we'll talk about that a little more in a second. All right. And then one of my favorites, like I said, is elastic potential energy. U is just kind of the prefix for potential energy. S stands for spring because anything that has this springy quality has a spring coefficient, and you stretch it some distance, and the farther you stretch it, the more energy you get. And so let's consider the redneck slingshot, which I'll show you a video here in just a second. They have these thick elastic cords, and it requires a whole four-wheeler to stretch this a distance. So let's say that this has a spring constant of 4,000, and it is stretched a distance of, I don't know, what does that look like to you? Maybe like 15 meters? Sure, great. Let's say 15 meters. And so as they pull this redneck back, once he is right here about to be released, there's a lot of stored energy there. And we can calculate that exact amount as 1/2 times the spring constant of this thing times the distance that this redneck is pulled back. And so it's going to be 0.5 times 4,000 is 2,000 times 15 squared, which is going to be 450,000 joules, okay, as this person is pulled back. Now you are totally allowed to fast forward through this part of the video, but I really love slingshots, and so I'm going to take this time to show you exactly what this redneck slingshot is. I'm going to keep those for now. Alright, and just sit back and enjoy, and if you want to, you can skip ahead in the video 2 minutes and 56 seconds. You can look this up on YouTube anytime. It is called Human Slingshot. Alright, so I love this as an example because it's a really good kind of impractical application of everything we've learned so far. This is not only a conservation of momentum problem, that the total mass and velocity beforehand is equal to the mass and the velocity afterhand. Think of this initial mass being very big, the person is released, mass gets smaller, and so the velocity gets bigger to conserve that momentum. It's also a really great example of the conservation of energy. So we have this elastic potential energy that is then converted into kinetic and gravitational potential energy. And it's just an overall really good example as far as physics goes. It is my duty and my responsibility to tell you please don't try this at home. However, if you find out where in Utah this is, you've got to tell me. I want to do this so bad. Again, please, please, please never try this at home, but the whole thing's a hoot. And so I'm just going to let the video play, you enjoy, and we'll get back to physics here in about, a minute or so. Alright, so back to physics. That's a great segue into energy transformations, which is that all of these different kinds of energy that we just talked about can change from one form to another. And so kinetic energy can change to gravitational potential energy, and gravitational potential energy can change back to kinetic energy. All of these can then go into chemical and electrical, electromagnetic, and sound. And so I kind of just want to use those terms of the different kinds of energies and talk about the transformations that take place with different objects. And so a fan is a great place to start. What does a fan absolutely have to have in order to work, no matter what kind of fan it is? Right? And so fans start with electrical energy, and that electrical energy gets converted into kinetic energy in the motor. After the motor runs for a while, that some of that kinetic energy in the motor gets converted to sound energy, and some of it gets lost as heat. Right? If you have a fan that's been running for a while and you touch the motor on the back, it's warm. And so not 100% of that electrical energy gets converted to kinetic energy. Some of it gets converted into sound and heat, which are lost to the system, and we would call this inefficient. For the rest of this chapter, we're really just going to assume that things are completely 100% efficient, and then we'll kind of look at this concept of inefficiencies in chapter 11. All right, so energy transformations. I want you, to the best of your ability, trace where this energy starts and where it ends in a flashlight. And you can pause the video. I'm going to go ahead and do that. And so all flashlights that I know of, pretty much all of them at least, require batteries, which are a form of chemical energy. That chemical energy gets converted to electrical. That electrical energy gets converted to electromagnetic energy, and some of it is lost as thermal energy or heat. All right, same thing with the runner. Go ahead and pause the video. Try and come up with your energy transformations for a runner. And I'm going to say that runners start with chemical energy. All good runners or athletes know this, that a good diet makes you perform better because your body is able to efficiently convert the right forms of energy into kinetic energy. So chemical to kinetic. Some of that chemical energy, though, goes to heat your body. That's part of what makes you a mammal, is that chemical energy actually creates an internal heat for you, which is metabolism. And that is kind of, some of that is kinetic, so there's kinetic processes going on in your body as well. Or, in my case, some of that kinetic energy can go to sound energy, like I'm speaking right now and I'm moving. And all of those things are very connected. I want to take a second and talk about the conservation of energy. I kind of alluded to this earlier, that on a roller coaster, your kinetic energy here gets converted to potential energy all the way at the top. And so I want to know that, let's see, we'll say we have this cart with a mass of 2,500 kilograms and a hill with a height of 30 meters. Okay. And I want to know how fast this cart needs to go in order to just barely make it to the top of that hill. So how fast does the cart need to be going down here to make it just to the top of that hill with a 100% energy conversion? And so I'm looking at gravitational potential energy equaling the kinetic energy in the beginning. And actually, you know what? Maybe I need to rearrange those for clarity's sake, because it's first kinetic energy and then gravitational. So we'll say kinetic energy is going to equal the final gravitational potential energy. Take a second and try and recall for yourself the formula for kinetic energy. And it is 1/2 mv squared. Right? And then the formula for gravitational potential energy is mgy. Right? I am trying to find the velocity here, and so what I'm going to do is I'm actually just going to solve this out in terms of variables for velocity, right? And so I'm going to try and get this velocity by itself. So I'm going to multiply both sides by 2 times 2. That gets rid of this here, and then I've got mv squared equals mgy times 2. I'm going to divide both sides by m. And here they cancel, and they actually cancel over here too, so I don't even need to know the mass of the cart. And then I wind up with v squared equals gy times 2. V squared. To undo that squared, I'm going to take the square root. And so I wind up with v equals square root of 2gy. And so this thing needs to be going square root of 2 times 9.8 times 30 meters. 2 times 9.8 times 30 is going to be 588. And the square root of 588 is going to be 24.2 meters per second for that cart to get up that hill. 24.2 meters per second is pretty fast, but is it a reasonable number? Yeah, it is for a roller coaster. Think how fast you're going on those things. Right? Reasonable amount. With the conservation of energy, we find that energy can never be created or destroyed. It can only be transformed. And I've already told you that these are not 100%, but for now, right, in the ideal physics world, we'll pretend that all of the energy is transferred, right? None of it is lost to heat or sound or anything like that. And we just solved that problem. All right. I'm going to move on to this idea of work. And work kind of has two definitions. One is the change in energy from beginning to end of something. And so if the energy of a system is changed, then that is the work that has been done. So if I have a person who starts at 0 meters per second and they go up to 10 meters a second, then the energy of that person or that one system has changed. And that would be the work that they have done in joules. Sometimes, though, it's more beneficial of us to think of work as being some force applied over some distance. And again, this is newtons times meters, which is really just the same as a joule, right? So we'll give you this example, and I'm going to go with this definition, the force times distance one. How much work is done if I push on a wall with a force of 50 newtons? Right, so I know that work is equal to force times distance. My force is 50 newtons. And the distance that the wall goes, that's an interesting thing. So if I push on a wall, does it move at all? Well, no, it doesn't. Not if it's a decent wall that's worth its muster. So that wall moves 0 meters, which actually means that I've done 0 joules of work. And when we think about this in terms of change in energy, well, that's true. Could I burn calories pushing on a wall? Yeah, maybe. But ultimately, I haven't transferred any energy to that wall. I haven't made it move. I haven't made it do anything. And so you guys aren't going to like this, but if something doesn't move in the same direction that the force is being applied on it, then no work is done, technically, from a physics point, right? Is it hard for me to push on a wall for 50 newtons? Yes, it definitely is. But if I didn't move it, then I haven't done any work in terms of physics. Okay? And so let's go on to a situation where work is done. How much work is done if I, a 70 kilogram person, run up a 5 meter flight of stairs, right? And I'm going to clarify for you here, and I'm going to say that these stairs are 5 meters vertical, right? So like a flight of stairs. Not 5 meters this way, but 5 meters up and down. And so if I am 70 kilograms, and I run up a 5 meter flight of stairs, the force that I apply, right, is going to be my weight times gravity. So I'm going to do 70 times 9.8, right? This is going to be my change in energy, times the 5 meters. And this is my change in gravitational potential energy. So U sub G. And when I multiply that out, 70 times 9.8 times 5, I get 3,430 joules of work for me to go up basically a flight of stairs. And is that a reasonable number? Yeah, it is. All right. Going on to this idea of things that you're not going to like about forces that don't do work exactly. Just because it is hard or difficult to do, or in your mind, in lay terms, requires energy to do work, does not mean it actually does work in terms of physics. And so I double dog dare you to take your physics book and hold it out in front of you, like so, right? As long as you possibly can, and if that's not hard enough, then go ahead and stack things on top of it. But the trick is to keep your arms still, right? And then we'll analyze this in terms of physics. So the force you're applying a torque, right? And you can imagine that this box is, or the book is pulling down because of gravity, and so you're resisting that to keep it in equilibrium, and you are kind of applying this upward force. But at the end of the day, there is no movement, and there's no change in energy. This box is not gaining or losing potential energy, nor is it moving at any speed. And so if work is force times distance, and your distance equals 0, then your work is also equal to 0, right? Is it tough to do this for 6 hours? Yeah, you betcha. But if the book doesn't move, no work is done. The other thing that maybe you won't like is, if I am, let me change my colors. Let's say I am carrying something, like a box. So again, I've got the boxes kind of pulling down and I'm pushing up, but I'm also walking in this direction to the right. Even though the box is moving to the right, if the box is my system, how much work is done on the box? Well, none, because the force I'm doing is not in the same direction as the velocity in which I'm moving. And so yeah, while the box goes from point A to point B, it's not in the same direction of force, so I can't count it. And so if force and delta x, or the change in position, aren't in the same plane, and by plane what I mean is like the x plane or the y plane, then no work is done, right? Or I'm sorry, work equals 0, right? There is no work. And then the last situation in which no work is done is if nothing moves. So if I am pushing on a wall, I've got a wall and a person who's pushing, and this wall doesn't move, my distance equals 0, so my work also equals 0. Right? So for all three of these situations, if something is not moving, it's in equilibrium. If the force and the displacement are not in the same direction, then there's no work done. And if something is not moving, then no work is done. Right? Those are the three situations that are going to get you. All right. The last thing we're going to talk about in Chapter 10 is perfectly elastic collisions. In Chapter 9, we talked about perfectly inelastic collisions. And in Chapter 10, perfectly elastic collisions, perfectly elastic collisions are those in which things bounce perfectly, right? And they don't stick together. And so imagine that I've got mass 1 and mass 2, and 1. Oop, there we go. Oh, both of those look like 1s. Erase all. There we go. So let's say I've got mass 1 and mass 2. And 1 and 2. Right. In the last chapter, we talked about these two things colliding and then sticking together. We kind of talked about inelastic collisions, we kind of talked about elastic collisions where these two things collide, and then after they collide, They bounce off of one another. Perfectly elastic collisions, here we're going to go into a little bit more detail, and we consider both the conservation of momentum, right, which is mass times velocity, and energy. And in this case, we will usually be talking about kinetic energy, right? And so the momentum before something happens has to be equal to the momentum after that thing happens. And remember, for the total system. And the same is true of kinetic energy. So kinetic energy before something happens and kinetic energy after something happens are both equal. Energy is never created or destroyed, only changed. Momentum is never created or destroyed, only changed. On page 311 in your book, it begins to talk about perfectly elastic collisions. And your book tends in this chapter to focus on something that is sitting still, and it gets run into by an object, and then, so initially, right, and then in the after situation, both of these objects begin to move kind of in the same direction, so a perfectly elastic collision. In a perfectly elastic collision, we usually know the mass of the objects and the initial velocity. We assume that for the equations that I'm about to show you assume that the initial velocity of object 2 is 0, right? And so know that these equations assume that object 2 is the one that is not moving at first. And so, again, on page 311, you can see these in the yellow box. If I know the initial velocities of things, then I can find the final velocities of things. And so that top equation deals with object 1. The final velocity of object 1 is going to be equal to the mass of 1 minus the mass of 2 over the mass of 1 plus the mass of 2 times the initial velocity of object 1. So however fast object 1 is going before it hit object 2, that's the initial velocity of object 1. And then the other question we'll be asking is, okay, well, when object 1 runs into object 2, that was originally sitting still, how fast is object 2 going to be going? And so that's that second equation, is that the velocity of object 2, the final velocity of object 2, is equal to 2 times the mass of object 1 all over the mass of 1 plus the mass of 2 multiplied by, again, that initial velocity of object 1. If you want to know where these two things are coming from in these two equations, you can look above that yellow box, and there's a mathematical explanation of, okay, how is this a combination of the conservation of momentum and energy? And it's momentum and kinetic energy specifically. Alright, so we've talked about work, we've talked about energy, and now it's time to talk about power. Please, please, please throw out all common definitions of the word power in your mind. It is not powerful like the president. It is not powerful like strong. The physics definition of power is how fast work gets done, or how fast energy is transferred to something. The unit for power is the watt, and watt is another complex unit, and it's actually joules per second. And so 1 joule per second of energy is equal to 1 watt of energy, right? There's a few equations for power that make sense, just like there is for work. And so you're going to kind of choose your equation based on your situation. Power in watts can be the change in energy over the change in time. And so, as that person goes up the stairs, well, how fast do they get that done? Because going up the stairs in 3 seconds is a lot different than going up the stairs in 30 seconds, right? You can also think of it as force over distance, right? Work, the amount of work and how fast that gets done. Again, if I ask you to push a box across the floor, and you take 10 seconds to do it, that's a lot different than taking 2 seconds to do it, right? Work is just force times distance, so if you want to expand that out, you can. And then there's this really interesting idea that the change in position over the change in time, this component, is actually just the velocity. And so we can also talk about power as force times velocity. Okay? And depending on the situation, you might choose different ones to represent power. Okay? And I actually, let's see, I don't want you to worry about this or this. We'll do that in the next chapter. And so let's go on to your homework for chapter 10. Alright, and so no crying, no tears. Homework for chapter 10, and this is all of chapter 10 in one lecture, right, is the conceptual problems from, page 316, numbers 2 through 11, 14, 16, and 22 through 25. And then from the normal problems, you will do problems number 1 through 5, 7 through 9, 15 through 17, 22 and 23, 39 and 40, 41 and 42. And that'll complete all of chapter 10. And the code word for today's lecture that I'll ask you on Friday to see if you listened is Bazinga. Z-I-N-G-A. And if you've gotten today's code word, then you're ready to go. Right? Enjoy, have fun, and I will see you on Friday.